Good evening. Today I will be showing you the third question in the test for extra credit, and what will likely be question 3 and the extra credit for question 3 for test 4 in chemistry 1412. This question asks us to show that one compound is more acidic than the other. Two compounds are given, phenol and cyclohexanol. So whenever acidity is in question, the first thing that should be drawn is the conjugate base. And I've gone ahead and done that here for both of them. To break out of the habit that I feel like we tend to have, I'm going to go through each thing individually just to represent each, and then we'll talk about each of the differences in terms of determining acidity, like once I have both of them listed, and that is to kind of say, oh yeah, that's kind of to break the idea of saying that size, if there's a difference in size with the negative charge, if there's a difference, some people like to say that this one's automatically more acidic, although the entire problem should be shown out completely. So we're just going to go through all of these, list what the charge is, or yeah, you get what I'm trying to say. So, when drawing the resonance, just be sure to remove a hydrogen. Hydrogen can be removed from any of these carbons, although oxygen can be calculated to handle the negative charge better, so we just do that here. Don't have to show that part of the problem, but you do have to show other parts. So disregarding what I said earlier, because that was kind of a dumb way to open this up. How you determine acidity is comparing size and then electronegativity of first the negative charged atom and then the neighbor of the negative charged atom, and then resonance. So it kind of can't be done individually, but just bear with me here. So first things first, we have size. Now the negative charged atom here is going to be oxygen. The negative charged atom here is going to be oxygen. So comparing oxygen and oxygen together in terms of size, you have no difference. Thus, it cannot determine acidity. It is the same atom after all. Alright, so then we move on to electronegativity. First, we will compare the atom with the negative charge itself, which will once again be O versus O. And that has no difference, because again they're the same atom. They cannot have differences in electronegativity. And then we will compare their neighbors, which are two carbons. So, and two carbons don't have a difference, so once again those do not affect acidity. So this brings us to the main meat of the question, the most time-consuming part of the question, which is resonance. Now, the three things required for resonance are three atoms, of course. One needs to have a lone pair, and then there needs to be a double bond between 2 and 3. So looking back up at our conjugate bases, we can already kind of flag cyclohexane, as it doesn't have any double bonds, so there won't be any resonance structures here, which meaning, of course, then phenol is more acidic than cyclohexanol, but we have to, of course, prove that is the point. So by citing resonance, we can say that by the end of it anyway, we can say that phenol is more adapt, I guess, to spreading the negative charge than cyclohexanol is. So I'm just drawing the original structure just to start, and then there's no resonance here, so no real reason to draw it again. So I'm going to show you how to do resonance like once or twice, and then there are, like, I believe 5 resonance structures to this. yeah, there are 5 to this one, so it might be a little time consuming to do all 5 of them, but we'll see where we go. Anyway, so the numbering system goes as this. 1 should have a lone pair, and there should be a double bond between 2 and 3. So there's a double bond here, so I'm just going to mark this one as 2 and this one as 3. It fulfills all of the rules outlined here, so we can go ahead and move on with resonance. We can circle a lone pair at 1, move it between 1 and 2, creating a double bond, and then we could circle the double bond at 3, and between 3 and 2, and then give a lone pair to 3. Excuse me. Alright, so that completed structure will look something along the lines of this. So we still have that negative charge. Be sure to write the negative charge just so you can identify it. I actually didn't write it in my redrawing here, so that is a very important thing to write, because the negative charge is kind of important to the whole thing. That's why resonance is important in the first place. So we have 1 here because it has a lone pair. There is another resonance structure. We can have 2 here and 3 because there's a double bond between them. And we just repeat the same process by circling the lone pair, moving it to the bond between 1 and 2, and circling the double bond at between 2 and 3, and then moving it to 3. And so you'll end up with something along the lines of this. And these structures particularly, it is important that you write each double bond and each a lone pair especially. Most skeletal structures don't involve the lone pairs, so it can be tricky to determine where one is. We have a negative charge here. Now, because of I forgot to put the double bond here. I apologize. Anyway, we have the negative charge here, along with the lone pair. And then the double bond is now here. And so we have another structure available because this is a lone pair at 1. And then 2 and 3 has yet another double bond between it. So we can write that out once again. Hopefully I am careful to show you the correct process. The last thing I would want to do is confuse you. So we have the lone pair at 1 moving between 1 and 2. The double bond at 3, or between 2 and 3, moving to 3. And so we have a lone pair negative charge here. We have a double bond here. And then the 2 previous double bonds. There is one more structure, and you'll see it looks very similar to our first one here, but it is different. 1 has a lone pair, and then you have 2 and 3 up here with the oxygen, because there is a double bond between them. So the lone pair at 1, double bonds, it moves it to a double bond between 1 and 2. The double bond at 2 between 2 and 3 moves to a lone pair at 3. So you'll end up with this same 3 lone pair structure, but a little bit different, or a different arranging of the double bonds, as you will see shortly. So the double bonds are actually just shifted over a little bit, and that does make it a different resonance structure. Now the point of looking at resonance is to see how spread out the negative charges, because if a negative charge is more spread out, you can handle more negative charge, meaning it's more stable. And that, because we're looking at a conjugate base, we can say that the more stable base will have a stronger conjugate acid. So we can say, because of resonance, phenol spreads the negative charge. And, well, I should say, my apologies, the conjugate base of phenol, because phenol itself does not, you get what I'm saying. The conjugate base, which is what we've determined here, spreads out the negative charge. And that makes it more stable. And then phenol itself would be more acidic, because the more stable, the more closer to neutral you have in a base, the stronger the acid in turn will be. So because of resonance, the negative charge is more spread out, making the conjugate base of phenol more stable, and because of the stability of the conjugate base of phenol being stronger, or being greater rather, the acidity of phenol is also greater. Thank you for watching. I hope you learned something. Have a good evening.